improper integrals. Well, for you at least, in mathematics, I don't know about physics and other subjects, but in mathematics we deal with improper integrals. We only have two types of question, two types of problem in the improper integrals. The first kind of question is, does the integral converge or diverge? And we say, I'm reminding you right now, I'm simply doing a little bit a step back to recap. An integral converges if, despite this long infinite end or tail, if despite this we have a finite value, a real number value for the integral, then we say the integral converges. Because we add up tiny slices, but altogether they cannot exceed a specific given amount, which is obviously the area under the curve. And an improper integral diverges if we can exceed any previously decided number, any previously decided amount. In other words, the area is infinite. So divergent means the value is infinity, we can't find any specific value. Convergent means we can actually state a specific area value for that integral, for that area below the curve. Now, if the integral is convergent, if we can prove that the integral is convergent, then obviously we can find this value if we know how to integrate it. If the integral is divergent, then there is no use even trying to integrate it. Last time we saw that we tried to integrate some improper integrals and we saw, oh no, it's divergent, oh no, it's divergent. We were trying to get a value and we got infinity and we said, no way. So it would be nice if we could save ourselves some trouble and be able to look at the integral and say, okay, it looks like this will be divergent, let's not even try to calculate anything. That's why we use these convergence tests. Another reason is that sometimes this improper integral, it's not even important how much the value is. The only thing that is important really is that it does converge or does diverge. It's more for theoretical purposes. In theory, for academic purposes, it's important sometimes, it's important to know that the integral converges even without knowing what the actual value is, because that value seems not to be so important. Alright, so how do we test improper integrals? There are two basic tests, and then a third idea about, the third idea is about absolute convergence, absolute values. So we'll look at these tests. Okay, now, you have those papers, you have two comparison tests, comparison test 1 and comparison test 2, or comparison by ratio. The comparison test implies we decide the convergence or divergence of an integral by comparing it to another function, to another integral, for which we know whether it converges or diverges. Now, we need two things. First of all, we need to know how to compare two integrals, and secondly, we need to know how can we tell for some basic integrals whether they converge or diverge. And that's what we are going to do today. So the first comparison test. Let's suppose we have the given integral. I'm going to write this for type 1. Type 1, subtype 1. But basically this method works for both. This method works for both types. And so, from a to plus infinity function f of x dx. We want to know something about this integral. Now let's suppose the function f of x is a little bit complicated, it's not very nice, but we have something else, some other function, g of x, f of x, g of x. We have another function about which we know that it is no less than the function f of x in this part of the number axis. So from a to positive infinity. So for all, if for all for all x values greater than a, if for all values that actually apply to this integral, we have a function where we have another function which is greater than or equal to the function f of x. So why would we have it? Well, perhaps something familiar, something that's simple, something for which it is easy to state whether it converges or diverges. So if we have this function, and let me remind you, we are talking about positive functions only. So if we know another function about which we know the properties of the integral for this one, so now I can say that if the integral from a to plus infinity of the function g of x dx converges, then obviously I can say my original integral. I'm denoting it by I because I don't want to write too much. So if the integral of the greater function converges, then obviously the integral of the smaller function, the integral of f of x, must also converge. I hope it's understandable, because if I have some function about which we know that this integral actually converges, in other words, it's a finite number, it's not infinity, and then we have this f function, the given function, we have this f function, the given function, which is less than the j function. So if this area is a finite number, it's not infinity, then obviously the area below that lower curve is also finite. It cannot be infinity if the larger area is finite. So that I hope that's understandable. By the way, we can do it the other way around. If this integral, so if the integral of the smaller function diverges, so if the integral of the smaller function, in this case it would be this one, the integral of f diverges, then obviously the integral of the greater function must also diverge. In other words, if we look at the sketch, if this green area, this smaller area is infinity, then obviously the greater area also must be infinity. It cannot be less than infinity. So if we have two functions and we can compare them and we strictly know that one of them is less than or equal to the other, then if the integral of the smaller function diverges, then the integral of the greater function must also diverge. And on the other hand, if the integral of the greater function converges, then it sort of limits from above, bounds from above the other function, so the integral of the smaller function also converges. Now, the problem is, of course, always, how do we know, how do we find this function g? How do we find this other function? Well, actually, if we have a hunch, a gut feeling that our integral will converge, then we try to find a function that's greater than the given function. If we have a feeling that our integral must diverge, then we should find a function that's less than f of x and show that the integral of that function diverges. So the choice of the function, this additional function, depends on some general idea that we might have whether this integral converges or diverges. If we want to prove that it diverges, we need to find a smaller function whose integral also diverges. If we have a feeling that this integral must converge, then we have to find a greater function whose integral converges. How to find these functions, we'll consider that a little bit later. So this is the first comparison test, the simple comparison. Simple comparison. All we need is another function to compare to the original function. I will give you examples, but I want to show you the other method because I don't want to return to these two methods. I will, yes. There will be examples. Okay. The second comparison test number 2, it's also called the ratio test or comparison by ratio. In this case, you know that we can compare two numbers or two functions in many different ways. For example, which one is greater than the other one? But if we consider a ratio of two functions, we get something more important than simply telling which function is greater and which function is less. If we consider a ratio of two quantities, we actually are checking the commensurability of these two quantities. In other words, we are checking how these two functions can be measured one by the other. In other words, if I can consider a ratio of two functions, then obviously, if this ratio is a finite number, some number, 2 or 3 or 4, a finite number, then we must understand that these two functions are pretty similar. One function is simply 3 times greater than the other one, for example. But of course, that's no help because that would work only for function f of x and k times f of x. And therefore, we actually consider the limit of this ratio. So we can also call this the limit comparison test. Lim as x tends to plus infinity, limit of this ratio. So now, if the limit of this ratio is a real number, a finite number, not infinity and not 0, then we can say that yes, over there in infinity, these two functions behave in a very similar way. In a very similar way, if the ratio tends to be some constant, so one function tends to be, for example, 3 times greater than the other, then obviously the area below the greater function might be something like 3 times greater than the other one. At least as we approach the infinity, we don't know what happens here in the finite area we are considering. Now, if the f function, if this limit is infinity, then what we get that f function is much greater than the g function. It's infinitely many times greater than the g function, which actually doesn't tell us anything much because it's still possible for one of them to converge and for the other one to diverge. And if this limit of this ratio is 0, that actually means that the function f is many times, I would say infinitely many times less than the g function. And again, we can't tell much about the behavior, the behavior of these two functions. And therefore, if this limit of the ratio of two functions, in other words, again, we are looking for an additional function, for a complementary function, something that might help us, then we should look for something that is similar enough to the function f of x. In other words, so that we might hope that these two functions behave similarly. And so, if the ratio of these two functions is a number c, the limit of the ratio is some number c, a constant, but not 0, and obviously not infinity. C means a constant, infinity is not a number at all. So if we have a limit of the ratio, some non-zero constant, then it turns out that the integrals, improper integrals of these two functions behave in the same way. they both diverge or they both converge. In other words, if I have chosen the other function g again wisely so that I know whether that integral converges or diverges, then in this case I can actually state that, okay, then the integral of the f function does the same. And so if this is true, then the second comparison test, then the integral of the f function and the integral of the g function both converge or both diverge. In other words, they behave in a similar manner. Both converge or both diverge. So I have been writing limits when x tends to infinity because this is type 1 integral. The example is for type 1 integral. Actually, if I have type 2, it would be from a to b, let's say we have this uncertainty or infinity at the limit a. In that case, I would say x tends to a or x tends to b. In other words, I have to make x tend towards the danger point. In this case, it's infinity because if x tends to infinity, then the integral has this long tail which either converges or diverges. And in the type 2 integral, x tends to something finite, to a or to b, or to some point in between there, where the function value becomes infinity. So for type 2, it would be from a to b, and x would tend to a or to b. Well, it depends which boundary is the dangerous one. Okay, so this constant or ratio that approaches some constant, ratio actually means that these functions are similar enough for us to make this statement, that they both behave in the same way. The third property, the third test, which is not exactly a convergence test, sometimes we have to consider negative functions. So if I can take the absolute value of this function, in other words, in the third part, if I can put a modulus sign, the absolute value sign on that function, or rewrite this function so that I have a positive function by changing its sign, then I can say that if the integral of this positive function converges, then the integral of the general function also converges. It's called the absolute convergence, but we will generally not go into much detail for this. There are not many of you, if anyone, who might ever need that part. Alright, let's have a look at how to check and what are good functions to choose for G for comparison. Let's have a look. There are two types of functions that are very useful for this. For type 1 integrals. In other words, for a to plus infinity, f of g, f of x, dx. For this kind. There's one very good kind of function for which we can always tell whether it converges or diverges. In other words, if we choose g function 1 over x to the power b, where b is a positive number, in that case, we call this a p function. This kind of function, we call it a p function. That would be something like, for example, 1 over x squared, 1 over x to the fifth, or 1 over square root of x, because here p equals 1/2. So this kind of function, 1 over x to some power, even if this power is a rational number, even if it's a root. All we need to know that it's positive. So in this case, In this case, the integral from a to positive infinity 1 over x to the power p dx converges if and only if p is greater than 1. If p is greater than 1, then this integral converges. We will integrate and check and see what happens. And if p is less than or even equal to 1, the integral diverges. Less than or equal to 1. And we can actually check, well, we can look at this function using examples, or we can look at it more theoretically. Well, perhaps we can just use examples and not the theoretical analysis. I'm not sure if I have put this theory here. No, I haven't put the theoretical analysis. I have only put this example. So, the p function is actually the best function to use for testing type 1 integrals. Let's have a look. For example, from 1 to plus infinity, 1 over x to what power? 5. Let's take 5. Let's use a specific example. Let's show that this integral converges. So obviously the integral of x to the power minus 5 is x to the power minus 4 divided by minus 4. In other words, minus 1 over 4x to the 4th. Simply by integrating, the primitive function of 1 over x to the 5th is this. Remember that the power is minus 5, so when we integrate, we get exponent minus 4 divided by the new exponent. And now we have to integrate it between 1 and plus infinity. If I put infinity in there, it's 0. So we have 0 minus, well, if we put 1 there, it's a constant. So, okay, minus 1, 4. So we see that this integral actually does converge indeed. No problem with that. So the question is, how do we know when we will get 0 here and when we will get something else? Let's check those something else things. So for instance, let's take from 1 to plus infinity 1 over x to the power, well, square root of x dx, which means from 1 to infinity x to the power minus 1/2, yes, dx. So in this case, p is 1/2, which is less than 1. So this integral should diverge according to that law. It should diverge. Let's check. So minus 1/2 plus 1 is p to the power 1/2 divided by 1/2 means 2x to the power 1/2, so 2 square roots of x actually when we integrate this. We get 2 square roots of x purely by integration. Now what? If I try to put infinity in there, square root of infinity is still infinity. So it's infinity minus 2 diverges. So now the thing is, how can we be sure about this p equal to 1 being the boundary point, being the boundary between integrals that converge and integrals that diverge? If we have this number greater than 1, if we have this number greater than 1, then by integrating, this actually means that, all right, I'll try to do a little bit theoretically. So if I have 1 plus infinity 1 over x to the power p dx, which is, well, 1, okay, a, but What's the difference? Okay, I'll write a plus infinity x to the power minus b dx. Let's remember that p is positive and therefore minus p is indeed negative. So to integrate I need to add 1. So it's x minus b plus 1 divided by minus b plus 1 between infinity and a. And so the problem now is, what we need to see is, if x ends up in the denominator like this, below the line, then putting in infinity, we will get 0. If x ends up with a positive exponent after integrating, if it's above that line, if it's in the numerator, in that case, when I put infinity into a factor, we will get infinity. So the thing is, if this in the end goes below the line, everything is okay, the integral will converge. If this remains up there with a positive exponent, then this integral will diverge. So in other words, now we can see, what we can see is, if minus p plus 1 is positive, in other words, if x to this power is up there, x to a positive power, then what we have is a divergent integral, because putting in infinity instead of x will give us infinity. So this will be divergence, so that means that p is less than 1. If p is less than 1, I have a positive exponent, and therefore x being infinity gives us infinity. On the other hand, if minus p plus 1 is negative, then this means that this actually, to make it a positive exponent, I have to move it down below the line. I get 1 over x to the power p minus 1. So if p is greater than 1, then x is down there, and putting in infinity, we will get 0. Something divided by infinity will be 0. So this means it will converge. If you noticed, I didn't discuss p equal to 1 yet. If p is equal to 1, then the integral is actually the natural logarithm. The natural logarithm. So if p equals 1, then I have the integral 1 over x dx, which is ln. From a to plus infinity. And natural logarithm of infinity is also infinity. Because if you remember, the logarithmic function being the inverse of the exponential function behaves in the same way. So actually, yes, the logarithmic function slows down, but it still keeps increasing. It's not bounded from above. It can always reach any positive value that we want. Natural logarithm of very large numbers are very large numbers. So this is again infinity, and the integral diverges. So for type 1 integrals, it's very useful to have this function 1 over x to the power p. So as I said, we call it a p function. So when we need to prove or to explain why an integral converges or diverges, I can say apply the comparison test, compare to the function 1 over x to something. It's a p function. Because p is greater than 1, it diverges, and therefore the given function.
But how to compare it with the f function, with the given one?
Well, it's not so much the matter of how to compare it, but it's the matter of how to choose it correctly. Because comparison is easy. We are choosing it so that we know. We are choosing this function so that we know that this is indeed true. Let's have a look at some examples.
Could you please
Okay. This was simply an explanation. If you didn't follow, if you, I don't know what you were doing.
It's in the. Also. You can see video.
Yes. Sorry, I can't go very slowly because I can't. Go on. All right. Let's have a look. Let's have a look at first examples, indeed, that we have on the paper. From 4 to plus infinity, x minus 3 over cube root of x to the 11th power dx. Yes. Yes. Something like this, cube root of x to the 11th. This kind of function. Now, at the first glance, it's very difficult to tell whether this integral will converge or diverge. At least if you are not used to this, then it might be difficult. For me, it's not so difficult because I invented the example, perhaps, or because I know the trick, and I'm going to tell you the trick now. All right. So actually, the f function in this case is the given function, of course, as always. This function is the f function. And now, if I can find a g function which is greater than this, such that it is a p function and converges, then I'm completely happy. So what I can do is try to modify this function. So the g function could be, for instance, cube root of x to the 11th, skipping the minus 3. What happens if I forget the minus 3? It will be greater. This is greater because this is less. If I don't subtract 3, this is greater. And this consists of pure x powers, so I can rewrite this as an x power. So this is actually, because, okay, I rewrite it in a more obvious way. This is x, this x to the 11th under the cube root means x cube times the cube root of x squared. If you can do it like this, or I could rewrite this as 11 over 3 and subtract the exponents. That's another possibility. So I can think about it like this, so change the radical into a simpler form, and now I can see that this is 1 over x squared, cube root of x squared again. So now I can see that the total exponent will be greater than 1, very obviously, or I can write this as x over x to the power 11 over 3, which means I can divide both the numerator and the denominator by x again, but this time it looks a little bit more understandable. So I would advise this approach. How do I divide this by x? Minus exponent 1.
Yeah.
1 is 3/3. So this becomes x to the power 8 over 3. This is the same. 2 and 2/3. 2 and 2/3. 2 2/3, it's exactly the same thing. So now here, this is a p function. P function, and p is 8/3, which is greater than 1. And therefore, I know that, because I know that the integral of this p function, of this new function, 1 over x to the power 8/3 dx, converges from 4 to plus infinity, because the integral of the greater function converges, according to the first comparison comparison test, the given integral of the smaller function also converges. Therefore, integral of the given function
This one here.
for dx also converges. So this proof or this investigation consists of two parts. First of all, we have to choose an appropriate function for comparison, appropriate p function for comparison, and secondly, apply the comparison test. Choosing the p function can be, well, it can be roughly estimated like this. Ignore everything except the greatest powers of x. Remember, we did that for limits. When we did limits, and we had to find limits of some kind of quotients, we said, okay, let's divide by the greater power of x. So here it's the same. Ignore everything else because nothing else matters. The greater powers of x only matter because we are basically thinking about what's going on in infinity. We are not writing the limit explicitly here, but we are thinking about what's going on in the infinity. In the infinity, the smaller components don't matter. Only the greatest power in the numerator and the greatest power in the denominator matter. So we simply look at it like this. So if I have some polynomial in the denominator and some polynomial in the numerator, I can actually approximate the g function for p functions. I can approximate it by simply comparing these powers or simplifying something that consists only of those powers. There will be only one power in the numerator and one power in the denominator if you forget everything else. So sometimes it will converge and sometimes it will diverge and sometimes it will be greater than f and sometimes it will turn out to be less than f. So in many situations the second comparison test, this limit comparison, the ratio comparison, actually works better because it's easier to compare. We don't have to think, will this be greater, will this be less, for example. That might cause problems, and sometimes if you get stuck with this first comparison test, then by all means attempt to use the second comparison test, which is in many cases it's more efficient. Second example, from 1 to plus infinity, only just dx, 7 plus 3x squared plus 8x to the fifth.
Yeah, but that's the point.
Yes.
We will be given just one function and we ask it's converges or diverges, or we will be given
You will have, well, you will have not terribly many, but you will have some integrals that are easy to tell whether they converge or diverge, and then you will have one that you will need one integral for the convergence test for one of these comparison tests.
It's like,
Comparison test, one integral.
if here we given one function and asked it's just converges
Yes.
or diverges, we can build the greater function, yeah? Like to compare.
To compare?
Yes.
Yes. You can, well, but again, it doesn't work always in the same way. You have to be very careful how you find the g function. With what you compare this. All right. Yes. Last line. Remember the first comparison test. If I have two functions like this, and in this case I found this function and I said this will be my g function. And then I have this comparison test. If the g function is greater than the f function and the g integral converges, then the f integral also must converge.
So we substituted the
Which?
The power. What is that?
What if this diverges? In that case, if you see that this diverges, then a good idea is to take the second comparison test, because sometimes you have unfortunately chosen something that diverges, and perhaps you need to find a smaller function than f which diverges, and then so it might show that the f function diverges. Or if the greater function diverges, the smaller function might still converge, and therefore the second comparison test is actually in some situations better. For example, here, let's see how we can compare, how we can find the second comparison test useful. So the f function for this example is 1 over 7 plus 3x squared plus 8x to the fifth. Like this. As I said, let's ignore the greater powers. Let's only look at let's ignore the smaller powers. Let's only look at the greatest power possible. It's x to the fifth. So let's compare it to 1 over x to the fifth. If I had a polynomial here, for example, x squared plus 2 plus 3x, I would take the highest power from here as well. So now I'm only looking at the greatest exponents, and I say, okay, let's see what this function does. This is a p function. P is 5, greater than 1, so the corresponding integral of this function will by all means converge. And now I'm going to show you by the ratio comparison test, by that second comparison test, that both integrals, the integral given and the integral of this g function, both converge, both act in the same way. So I'm writing the second comparison test. The second comparison test, f ratio to g as x tends to infinity. So okay, I write the f function lim 1 over 7 plus 3x squared plus 8x to the fifth. X tends to infinity. Divided by g. Divided by this means multiply by x to the fifth only. Now, this is something from the first semester. You should be able to tell me what this limit is. It's 1/8. It's 1/8 because if we divide both numerator and denominator of this by the highest possible power, this is why we needed the highest power only. If we divide by the highest possible power, then by simplifying we might be able to find the limit. So in this case the limit is 1/8, which is a constant and not equal to 0. This means, according to, by the second comparison test 2, by second comparison test, the given function and this function, which we chose to be our g function, behave in the same way. So by second comparison test, as the integral of 1 over x to the fifth converges, then the given integral of the given function f of x, I'm simply too lazy to write this quotient, I'm writing it f of x dx, then this function must also converge. That's according to the second comparison test. So two parts absolutely necessary both. The first part is find a good g function, which is usually, and we won't consider any other functions, we really need mostly these power functions only, just powers. So evaluate the highest power in the numerator, the highest power in the denominator, omit everything else, skip everything else and simplify, and you will get the g function. It's not the same, but this is how we might guess the g function. And then write the ratio of the two functions, the given function and the g function, find the limit, show that this limit is a number, not 0, but any other number. And then all you have to do is state that according to the second comparison test, both integrals will behave in the same way. Because this is a p function and p is greater than 1, I can explain, because this is a p function and p is greater than 1, therefore, according to the second comparison test, this function must also converge. If by chance you get this g function, the p value less than 1, then obviously this integral would diverge. If you had, instead of 5, you had 1/2 or 1/3 or even 0.75, then you would say, oh yes, this integral diverges, but because by the second comparison test, both integrals have to behave the same way, the given integral also diverges.
This one is done.
So this comparison test is actually more convenient than trying to use the first comparison test. Although in some simple situations, the first comparison test is actually very good. But if you want to be sure, so this is more universal. The second comparison test works more universally and it's usually easier to deal with. So this was type 1 integrals. Now we need to have a look at type 2. Now we need to have a look at type 2. So for type 2, there's another type. P functions won't work. P functions won't work anymore. For type 2, let's remember that type 2 integral is from a to b, f of x dx, and besides, well, let's assume that, or what could we assume? Let's suppose that as x tends to a, the integrand function tends to infinity. In other words, let's suppose that we have this type with a vertical asymptote at a. So this type of type 2 integral, this subtype. So the lower boundary is the danger point, the critical point. A is the critical point, the lower boundary. In that case, a very good function for comparison is the alpha function, which looks, alpha function, which looks like this, 1 over x minus a to the power alpha, like this. Like this. But it's the other way around with the alpha function. With alpha function, if alpha is less than 1, then the integral converges, and if alpha is greater than 1, then this integral diverges. So it's the other way around. For p function, p had to be greater than 1 for the integral to converge. For alpha function, if alpha is less than 1, then the integral converges, and if alpha is greater than or equal to 1, then the integral diverges. This is because we don't have infinity here. At the danger point, at the critical point, we don't have infinity here. We have 0 here below the line. Previously, we were looking at functions that have infinity in the denominator. But in this case, we are looking at 0 in the denominator here. By the way, if we have the critical point on the left-hand side, so if x tends to b, and the limit is infinity, in other words, if the situation is a bit reversed, so we have something like this at b, In that case, we have to say that, you see, x minus b would be negative because x would be to the left of b, less than b. And therefore, we have to use b minus x. Then we use 1 over b minus x to the power alpha to make sure that this is positive, to make sure that this difference is positive. Everything else is the same. Alpha has to be greater than 1 for this function to converge, and less than 1 to converge, and greater than or equal to 1 to diverge. The general idea is that a power function, any random power function, is only defined if the base is positive. So there are not many powers, so actually there are too many powers that you cannot find if this base, if x minus a would be negative. You can't find, for example, if x minus a is negative, alpha cannot be 1/2. You can't find the square root of a negative number. And therefore, if the upper boundary is the one where the divergence or convergence might happen, in that case, we write b minus x, simply to make sure that the difference is positive. So we subtract the greater number minus the smaller number. So remembering that x is between a and b, we can find that. And, well, again, in a similar way, it is possible to choose a function such that it can be compared, or the function that actually becomes the alpha function, which might be slightly more complicated, but the general idea is the same. The general idea could be the same thing. So we might perhaps have a look at example 4. I think, yes, example 4 is a good one. So in example 4, from 0 to 2, cosine squared x dx, something horrible, divided by, I promise not to give you any cosines or sines in the test for this. 4 minus x squared, and that's under the cube root. A function like this. A function like this, which seems rather complicated. I'm showing you a difficult example so that the rest would seem more easy. I'm not going to ask something like this from you in the test, but I'm simply going to show you how these things work. Okay, so we can see that 0 is not the danger point. Here we would get 0 in the denominator only if x is 2 or minus 2. Minus 2 is not interesting for us because the integral is from 0 to 2, so minus 2 is far, far away. It's not so important. So x equal to 2 is obviously the bad point. What I'm going to do is, alright, I think I am going to simply consider the function itself. So this is the f function, and I'm going to look at it separately from the integral, before integration actually. I am going to factorize it. Cosine squared x without dx, because I'm not integrating at the moment. Cube root of, now 4 minus x squared. 2 minus x, 2 plus x. And of course, because it's squared, then I have to square these as well, like this. So now I can write cosine squared x divided by cube root of 2 plus x squared, and times the other part, cube root of 2 minus x squared under the cube root. Why am I doing it like this? Why did I choose this? Why did I choose this? Because what I have done, I separated the thing that is not dangerous. This, well, perhaps we might not be able to integrate it right away analytically on paper, but anyway, this does not give us any dangerous moments, because this will always be a finite number. Cosine squared of x, that's finite, between 0 and 1. It's okay, it's a number. 2 plus x will never be 0, not in this segment between 0 and 2. So this is a good thing. So this will never be 0, okay, it can be 0, but it will never be infinity. No problem with this. This will never be infinity. This cannot be infinity, if you like. I put it like this. Now, I can consider this other function, which means, so this is cosine squared x, I'm still writing the 2 plus x squared times, what is this? This is 1 over 2 minus x to the power 2/3. This is an alpha function.
What?
This is an alpha function, this kind of alpha function, because it was the upper boundary that gives us problems. It's the upper boundary that gives us problems, so I have this kind of alpha function. But it's alpha function. Alpha is equal to 2/3, it's less than 1, and therefore, now of course I have to look at something like this. I will choose my g function for comparison to be this. This will be my g function for comparison. And now all I have to do is take the original f function, take the original g function, and make sure that I can say that the limit is a constant, but not 0. And then I will be able to say that because the integral of this function is convergent, the integral of the given function is also convergent. So now I am again going to apply second comparison test or limit comparison test. So now, if my second comparison test tells me if the limit of f of x, g of x is a constant as x tends to, now remember, for limit comparison test for type 2 integrals, I had to make x tend to, not infinity, but to the dangerous point. The dangerous value was 2. This is the dangerous value. So x tends to 2. I'm writing it because it is this part that makes the whole danger. So if the limit of the ratio of these two functions when x tends to 2 is a constant, then because this function, the g function, has a convergent integral according to the comparison test, then the f function must also have a convergent integral. So all I have to do is now show that the limit of the ratio is indeed a constant number. So lim f of x, all right, cosine, well actually if I divide f function, the f function, this function, by this function, I actually get just this. If I divide this f function by g function, which I have chosen to be 1 over 2 minus x to the power 2/3. I simply divide out this factor. What remains is this. The ratio is just this. Cosine squared x divided by cube root of 2 plus x squared. This. Because this simply cancels out when I divide by. And x tends to 2. what do I have here now? Cosine squared of 2. I don't know how much it is, but it doesn't matter. And this is the cube root of 2 plus 2, 4 squared, 16. Okay. It's not 0. This is not 0. This is something, but honestly, I don't care what it is, as long as I'm sure it's not 0. It's not 0, it's not infinity, it has a finite limit. This ratio has a finite limit. So now I can say that because the limit of the ratio of the given function and my g function is a constant, whatever constant except 0, then I can state that the integrals of g function and of f function behave similarly. And because the g function is actually alpha function with alpha less than 1, the integral of g function converges, and therefore the integral of f function also converges. So because this integral from 0 to 2 of g function converges, it means that integral from 0 to 2 of f function also converges. This is useful in situations where we do not have to evaluate integrals. Because if we really had to evaluate that integral, find its value, then I would say, where's my graphing calculator? And that's all. I wouldn't even try to integrate it analytically on paper. I would put it into my calculator or into my computer and let it do the work. Because that's so theoretically, mostly in these cases, what interests me in this situation was how can I decide, how can I determine whether this integral converges or diverges? That's the general question. So perhaps we need a little bit of plan. So the first thing is find an appropriate g function. Find an appropriate g function, usually by comparing powers. In this case, there was a lot of extra stuff to mess things up and to make things more confusing in this case, in this last example. But generally, usually by comparing powers. You can write it down. Usually by comparing powers. For example, I could write something. X cubed plus 2x minus 1 divided by x to the 4th plus square root of x. For example, if the f function is this, then I could say, okay, let's forget the lower powers, and let's take the g function, x cubed over x to the 4th, only the highest powers. So, g function would be x cubed over x to the 4th, so it's 1 over x. Because when you divide these functions, f divided by g, you can see that these highest powers will cancel out, and here we will get those 0 things. That's, if you look at the limits, how those limits work, you will see that the ratio tends to some constant. You will see that this ratio tends to some constant. In this case, it will tend to 1, because if I divide this by 1 over x, it means I multiply this by x, so the limit will be 1. So first thing, find an appropriate g of x. To do that, we compare the powers, and usually we simply choose the greater powers. That's for type 1, at least for type 1. For type 2, we have to consider this a little bit. So after we find this appropriate g of x function, then the next step is show that limit f of x divided by g of x is a constant and not 0 when x tends to infinity in this case. And then write the conclusion. And then write the conclusion. Write the conclusion. Because the integral of gx dx a plus 1 converges or diverges. Converges or diverges. It depends on what you have got. What kind of p function? Because the new integral converges or diverges, the original integral, the f function integrated, does the same. I have a does the same. So this is basically the plan for using the second comparison test, which is generally the better comparison test to be used. Now I will erase this part. For the type 2 integral, we try to compare not x powers themselves, but we would need to do these x minus a powers. We would need x minus a powers. We should separate the highest x minus a power there, which is algebraically perhaps a little bit more messy. But of course, for the type 2 functions, this is what matters, because this was the alpha function was the one that's important for type 2. But basically, we find the g function by comparing powers of x for type 1 and of x minus a or b minus x for type 2, and then the rest works in the same way.
No, you write too much.
Okay, let's have exercise 7 perhaps. Let's have 7 because that's a good example. From 2 to 4. No, it's okay. I could find a better one. Let's do from 2 to 4. dx over 4 minus x cube root x minus 2. Like this. I'm afraid this will turn out to be divergent. Unfortunately. Actually, we can see that for this function, both ends are bad. Both ends are bad for this function. So we should perhaps split it into 2 parts. Because if x is 4, then this gives us 0. If x is 2, then this gives us 0. We get division by 0 at both ends, and that's what makes it bad. So I will split it into 2 parts, from 2 to 3, dx, 4 minus x, cube root x minus 2, plus integral from 2 to 4, dx, 4 minus x.
How did you decide to take 3?
Doesn't matter. Anything to split them. Anything to split it into 2 pieces. I could take 3.5 or 2.5 or 3.99. It really doesn't matter. 3 is a good number because it's an integer still, so we don't have to deal with fractions too much. So now I can see that for the first integral, only this x minus 2 is seemingly dangerous, and this will never be 0. This will never be 0. And for this integral, on the other hand, 4 minus x is dangerous. This will never be 0. So that means that we can deal with each of these integrals separately. Unfortunately, one of them will be divergent. So let's have a look at the first integral. The f function, therefore, is 1 over 4 minus x cube root x minus 2. In this case, because 4 minus x is not dangerous at all for this, because we have taken the 4 away, we separated, we left it outside. This is not dangerous at all. The only danger might happen for this. This is the one that creates that infinity. This is not dangerous at all. So for this, I will choose the g function to be 1 over x minus 2 to the power 1/3, which is this, the dangerous factor actually. We have to look at powers of dangerous factors. Powers of dangerous factors, which are what matter actually. So I'm ignoring this because like previously, it will change nothing. It will never be equal to 0. 4 minus x will not be equal to 0 in this segment. From between 2 and 3, it will never be 0. So I can take my g function like this. Now, let's do the limit comparison test. So f of x over g of x as x tends to 2.
To 2, yeah.
Because for type 2, we need the dangerous point, the dangerous moment. It's x tends to 2. Okay, let's have a look. Lim x tends to 2. Now, the dangerous factor cancels out. The dangerous factor cancels out. That's why we must always take the dangerous factor to the highest power possible to see that it cancels out. That's why I had to take this here. Because now I have, obviously, 1 over 4 minus x, x minus 2 to the power 1/3, divided by this means x minus 2, x minus 2 to the power 1/3 goes up. These two zeros cancel out. I have 1 over 4 minus x, which is 1 over 2. So the limit comparison test works for the first part. This is not 0. So this means that this integral and the integral of my g function behave in the same way. Because alpha is 1/3 less than 1, the integral of g function converges, therefore the integral of the f function, this one, converges. So the first part will converge. We have shown that the first part converges. Simply because we see that this is a constant, not a 0, therefore the integral of g converges, and by comparison test, integral of f also converges. Now the second part. Which is going to be a little bit sad because it will diverge. So for the second part, f of x is still the same, 1 over 4 minus x, cube root of x minus 2. Now for the second part, this is not dangerous because between 3 and 4, this will never be 0. This will never make a 0. And therefore, for the g function, we only choose the dangerous factor. 1 over 4 minus x for the g function. Because this will never be 0 in this segment, so it's not dangerous at all. We are only looking for the dangerous factors. And in type 1, the dangerous factor was x itself, x powers. Here, the dangerous factors are x minus boundary powers. Only dangerous powers need to be considered. So now, obviously, again, we look at the limit as x tends to, now in this case, 4 is the dangerous point. For the second integral, x tends to 4 of f over g. If I take this divided by this, I just get 1 over cube root of x minus 2 when x tends to 4, which is 1 over cube root of 2, obviously, if I put 4 instead of x. So again, This is a constant again, not a zero, which means the integral of f and the integral of g behave in the same way. What the integral of g does, the integral of f does as well. So, again, by comparison test 2, integral of f from 3 to 4 dx and the integral of g dx from 3 to 4 both do what? Diverge.
Converge.
No. No. Diverge because g, in this case, the UG function, 1 over 4 minus x to the power 1. Alpha is 1, which means divergence. Unfortunately. Both diverge because g is alpha function with alpha value equal to 1. Again, this is an integral and we have to split it into two parts. I promise I'm not going to give you integrals to be split into two parts in the test. At least not for testing convergence or divergence. Only if you have to explain why this is an improper integral. Yes, there is a question in the test. Explain why this integral is improper. You are not asked, at that point, you are not asked to evaluate it or tell whether it diverges or converges. Simply explain why is it improper. So you have to find the infinity, in other words. You have to find the infinity, where the infinity is. And, well, I have actually set up the questions for improper integrals in such a way that you don't have to do too much in each question, just testing little things. Okay. The examples are mostly type 1. Yes, but you will have, of course, some example of type 2, but not something very awful. I have sent you the solutions, but if you need more explanation for the exercises, because I believe that I simply gave you the answers, converges, diverges, for this exercise. So if you want to have more explanation, then you can email me and ask.